Okay, so we talked about the fact that when we compute the signed area under a curve, that gives us the accumulated change of that function. But sometimes we have curves that are actually curved instead of made up of straight lines, and then it's not so easy to compute these things using the shapes that we were using before, that we know how to take the area of. So what we can do is just approximate the area using something that's easy to find the area of. And one of the easiest things to find the area of is a rectangle, right? So what we're going to do is approximate the area under this curve. This is f prime, so this is supposed to be a derivative. And we're going to approximate the area under this curve. And so a common way to do this is either to use, so we'll use rectangles, we'll use a certain number of rectangles, and then we'll make them all the same width just to simplify things a bit so we don't have to worry about having variable widths. And then we'll just add up the areas of those approximating rectangles to get an approximation of the area underneath the curve. And so always we will use n to denote the number of rectangles when we're referring to this process. Number of rectangles. And then the width, the width of each rectangle will denote that delta x. And so this is the width of the rectangles, of each rectangle. Maybe I'll write that up. Width of each rectangle, right? And remember that we use delta x to denote change in x. And so you can see once we start drawing these that it's going to be measured along the x-axis, the width. And so it is somehow measuring the amount of change in x related to this approximation. Okay, so here we want to use, or we're going to use 5 triangles, or sorry, not triangles, rectangles. We'll use 5 rectangles to approximate the area. And so this will be starting from -1, we'll go all the way up to 4, and we'll just jump by 1 each time. So focusing on this first interval from -1 to 0, the approximation using left endpoints, what that means is that we take the left endpoint, which is -1, we follow that all the way up to the curve, and then whatever height that is, we then draw a rectangle that is that height all the way along the entire interval that the width that we're using, okay? So here is our first approximating rectangle, and we use the height of the function at the left endpoint, so that's what this left endpoint refers to. Next, we have the interval from 0 to 1. We do the same thing. We follow from the x-axis all the way up to the curve, and then we draw a rectangle at that height, and then we complete it. Right, so we have 2. The next one, the curve is below the axis, so we follow from the axis down to the curve, wherever it meets the curve, and then we draw a rectangle of width 1 right there. Right? So just to make this clear, I'm going to shade these in as well. So that's our first rectangle, second rectangle, third rectangle, and then next we have the interval from 2 to 3. Now notice that the function at 2 is equal to 0. So actually here our rectangle has 0 height, so that's fine. It can be like that. It's just not going to add anything to our approximation of the error, right? Area, not error. Okay, and then lastly we have one more rectangle. One more rectangle to draw, and so that would be this one right here. So there are our 5 rectangles, and then if we want to approximate the area, we simply add up the areas of each of these rectangles. So our approximation of the area will be, I should maybe put this down here where I have more room to write. So this isn't the exact area under the curve, it's just an approximation. But let's see, the area of the first rectangle, that has height 3, they all have width 1, so really we just need to figure out what the heights are going to be. So that one has area 3, the next rectangle has area 2, the third one has area -1, so since it's lying below the x-axis, it has a negative area. Because we're computing the signed area, remember? The fourth rectangle has area 0. We'll just write +0 to remind ourselves of that. And then the last one has area 2. And so adding these all up, you will get 5. Is that right? Wait. Let me actually do this. 3, that's 7, so 6. Okay. Okay, so that is our approximation. And just to be complete, so the number of rectangles that we used in this approximation was 5, and the width of each of them was 1. So our delta x was 1. Right? Okay. And we can do the same thing just using the right endpoints. So here we're going to use the same number of rectangles. So we're going to use n equals 5 over the same interval. So our delta x is going to be 1 as well. So the only difference between what we're going to do here and what we just did is just that we're going to use the right-hand side of the intervals to find the height of the rectangle. So starting from -1 to 0, we start at the right-hand side of the endpoint, or right-hand endpoint of the interval, right? And we just take this, we follow it up to the curve, but now we draw our rectangle in this direction, right? So for this interval from -1 to 0, we used the right-hand endpoint to find the height of the rectangle. And so that's going to give us this rectangle right here. And then we do the same thing for the others. This one is negative, so following from the x-axis down to the curve, and then drawing the rectangle right there. Here in the third one, that's where the function is equal to 0, so that means that this whole side, or this whole rectangle has area 0. And then at 3, we follow up to the function, draw a rectangle, and then lastly we have this last one, which looks like this. Okay. Great. So this is what our approximating rectangles look like. And then we can compute the approximation of the area. And that will be equal to, here our first rectangle has height 2, second one has height -1, 0, 2, and 4. So in this case we get 7, right? And we used n equals 5, delta x equals 1. Okay, so just looking at both of our approximations, honestly, when we're looking at these, they don't look like great approximations of the area under the curve. There's, if we look at the first one, there's all this area right here and here that we're not counting, and that seems like a big amount of error in our approximation. And then over here on this one, it seems like we're over counting with these two big rectangles, right? But then still undercounting over here. So, does it add up to being a good approximation? Probably not. So what we can do to get a better approximation is to use more rectangles. So if we use rectangles that are slimmer or have like a smaller width, then we can get a better approximation. So let's go ahead and do that. We're going to use left-hand endpoints. And so we're going to use twice the number of rectangles in this case. So before we used 5 rectangles, we're going to use 10, and they will each have width 1/2. Okay, so we'll go through this one a little bit faster. So using left endpoints, I'm just going to draw the rectangles in here, like so. And here. Wait. Okay, so now that we have all of those drawn, I'm going to shade them in just so we can really see what's going on. Right, we have all of these rectangles. That one is height 0. Okay, so this is what our approximation would look like, and we can see that it does look a bit better than what we had before, right? It looks a little bit closer to actually approximating the area under the curve, and so we can see that most likely if we were to use even thinner rectangles with an even smaller width, or more of them, in any case these two things are related, so we can think of it in either way. But if we were to do that, we get a better and better approximation. And so this should remind you of this idea that we had earlier when we were talking about defining derivatives, and that we defined secant lines. They weren't exactly what we needed in order to find the instantaneous rate of change, but they were an approximation. And how we actually got an actual answer for the instantaneous rate of change was we took a limit. So you can expect that we're going to be able to get an exact answer for the area beneath a curve, and the way that we do that is by using limits. And so we were not doing that in this section, but we will see it in the next section. Okay, but for now, I wanted to go over some sigma notation. Now, if you are really, oh, I noticed I didn't do the area approximation. I'll leave that up to you. I guess this is actually equal. So you can fill that in with the values. Right, so I wanted to talk about sigma notation. If you are very familiar with sigma notation, you can just skip to the next video, because that's all I'm going to cover for the rest of this video. Okay, so sigma notation is also referred to as summation notation. This means exactly the same thing. And it is just a compact way of writing down sums. Okay, and so it's just going to be a shorthand notation, and it's really nice because otherwise we would have to be writing out these really long sums and copying them down over and over and over, and that would be really annoying. So this is a nice way of writing those down. Okay, so what they look like are, we have a Greek letter sigma. This is a capital sigma, and it's sigma is the Greek letter S, so it stands for summation. So if you, that's the reason why we use this letter. Okay, and then we have what are called indices. So I will mostly use I as this variable. So this is saying that I starts at 1, so this is our starting point. Okay, I'll write that in a second. And then it ends at n, so these are our two bounds. And we are summing, the thing that we are summing is ai, and that is going to be just something, some number that depends on I, right? So this is going to be what we do to actually evaluate this is we plug in I equals 1, that's where we start, and then we add to it, because remember this is about writing down sums, we add the next number, so we jump up by 1, that'll be a2, and I'm assuming n is, you know, a decent amount larger than 1, and a3, and so on. And then since n is our stopping point, we stop when we reach n, right? So that is the definition of this sum. Just to emphasize, ai is a number that depends on I, right? So we'll see an example in just a bit, but just one thing, as I said, this I equals 1 is your starting point. So this means you start at 1 and you end at n, and the two of these together, the top and the bottom, these are called your bounds. So your bounds of your sum, okay? And remember that you always increase by 1. So I'll just put this off to the side. You always increase by 1 with each step. By 1. Okay, so let's see an example. Okay, we could have, so I will actually have an actual number for our stopping point, so I equals 1 to 5, and the thing that we will be summing will be 2 to the I. And see, if we replace I with a number from 1, between 1 and 5, then we get a number, right? So this is going to represent the sum 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 5, right? And we could sum this up and get an actual number for this, but I'll skip that part. So this is just the meaning of this, so the sigma notation. We can have, I does not always have to start from 1, even though I wrote it that way. A lot of the time it will start from either 1 or 0, but it doesn't have to. This notation we can, you know, use to write down sums that say start from -1. Okay, that's perfectly fine. We can use that as a starting point, and then let's say it ends at 7, and then we just increase by 1 with each step. So oh, oops, I didn't say what we were summing. So let's say we're just summing I itself. Sorry, I'm writing tiny because I want to fit one more example in here as well. So -1 would be our first number, and then we jump up by 1, so that would be 0, and then we add that because our expression is just I by itself. And then we add all of the numbers between 1 and we stop and 7. So we stop at 7, right? And so you see that this is a much more compact way of writing that sum out. What's even nicer about this summation notation, which is it is that we can have an arbitrary stopping point. So just like how we wrote the definition, we could leave this as an arbitrary number n if we don't want to actually specify what n actually is, right? So instead, let's say we had two, or I'll do this example, this is fine. Okay, so we can have just one. Now notice that the thing that is in our sum, the thing that we're summing, does not depend on I, but that's okay. It just means it's not going to change with each step, but what is going to happen is we're going to sum 1 each time we make a jump, right? So for the first term we get 1, for the second term I equals 2, but that doesn't change the thing that we're summing, we still got 1, and so on. And so we'll actually have to add a 1 for each index from 1 up to n. So we're going to have to add 1 to itself n times. Okay, so that means that the sum from I equals 1 to n of just 1 by itself is equal to n, right? So be careful of this because you might expect when you look at this sum that it would be equal to 1, but we actually have to add a 1 for each step that we make, and so it's actually equal to n, right? And like I said, this is an arbitrary length. We didn't specify what n is, and so this gives us a nice way of writing down this type of sum. Okay, so that is all for the sigma notation, and then we are going to talk about Riemann sums in the next video.